we have the xn conversion in distribution to C, okay? We need to prove that, right? xn conversion in probability to C, right? So in order to do that, right, we need to know what we have and what we need to do, right? So what we have is that fn x, right, converge to fc, right? So in this case, the x will be a c, okay? Yeah, x will be a c, just a constant. So basically now it's just pretty much like a step function, okay? So step function, it jump at c, right? So basically like before c, it's 0, from c is 1, right? C is 1. This is a step function, okay? And we need to prove that. So this we have, okay? This we have. We got, right? We got it. And remember the fcx here, it will be a step function, okay? Step function. So jump at c, okay? And we need to prove that, right? We need to prove that conversion in a probability, which means for any epsilon non-negative, right? A given epsilon, and you need to show that, right? Xn, the distance between Xn and C, okay, greater than epsilon will go to 0, right? So this is what the goal here. So if we can prove that, and then basically we can show this conversion in probability, right? So basically like star equivalence, we like need to prove that, okay, for any epsilon non-negative, and you have the distance between the Xn and C bigger than epsilon will go to 0, right? So basically like it's just you can see it close to C with a high probability, right? High probability. It's far away from C with very low probability, right? This probability go to 0. So what is this quantity, right? So now we need to try to make some extension about the quantity probability xn subtract C absolute value greater than equal to epsilon, okay? So this quantity is will be equal to xn, okay, less than equal than C subtract epsilon, and plus, okay, plus xn greater than C plus epsilon, okay. So this is nothing new, it's just you make the absolute value, sorry, this is epsilon, not C. So you just take out, you know, the take out the absolute notation, and you should get these two, right? In these two side, either xn less than C subtract epsilon, xn bigger than C plus epsilon, okay? And this guy is nothing else than just these two guys, nothing else than, you know, just the CDF function of fn, fxn, right? Fxn. So basically, the first term is just the fxn of C subtract epsilon, which is so. Okay, I write it here again. Xn subtract C epsilon will be equal to the first guy is, okay, the first term here is nothing else than the fxn C subtract epsilon, okay? In the second term here, you just it's just a 1 subtract fxn C plus epsilon, okay? The second term you can rewrite in this way. 1 subtract fxn C plus epsilon, okay? And because because we did have, right, because we did have that, right? We did have like maybe we call maybe 1 because of 1, right? Because of 1, right? Because 1, right? 1. So we have like because 1, right? We got because maybe from 1, maybe from 1. right? From 1, right? We got fxn c subtract epsilon will converge to fxc subtract epsilon, right? Uh, we have for any x is whole, right? So which means this guy is also whole. And this is because it's a step function, right? fc, in this case, yeah, x equals c, okay? So maybe I put it here. X equals c, okay? X equals c, okay? So I didn't know another x, okay? Okay, transition. You look at it, it's just a constant, right? X now is a constant. And basically, this is just zero, right? Because x equals c, and which means at before c, we should have any weight there, right? We should have any weight there. So it will be 0. And fx and c plus epsilon equal to fx c plus epsilon, okay? So which is like c, a little bit more than c, right? And this guy is 1, right? 1. Remember, x is a constant. So fx x is just step function at c, okay? And the step function basically before c is 0, and from c and above is 1. Okay, that is what step function go, right? So the step function is like this, right? So you have c something maybe here, right? So everything here is just 0, but at here is jump, okay? Jump to 1, okay? So this is how the fx x function go, right? It's a step, it jump. So because that thing, right? And we have that. So basically now we plug in, right? So plug into maybe 2 star, right? So plug into maybe plug maybe 2 and 3, right? 2 and 3 to 2 star, right? 2 star. So we get thus the property xn subtract c will be equal to, will converge to basically 0 plus 1 subtract 1, right? And so you get 0, right? 0. So in other words, we did prove that. So in other words, right? So for any epsilon positive, we show that, right? We show that from the xn subtract c epsilon tend to 0. In other words, right? In other words, we have xn conversion in probability to c, okay? So we just finished the proof for probability 2, right? So if conversion in distribution to a constant, it will lead to the conversion in probability, right? So how about the so maybe your job, okay? Just look for a counter example, okay? Example. I may give it this problem in a test, okay? Counter example that xn converts to x, okay? X here not random, just random variable, not constant, okay? Not c, not constant c. But right, but xn it won't happen, okay? So we just show that in the probability 2, right? Xn convert in distribution to a c constant, and then we get that direction, right? We get that proof, right? But how about say, it just converts to anything, right? Maybe any random variable, if not constant. And other time, this probably will be violated. Okay, so this is your task. Okay, find it. Okay, I will give this problem in the test too. Maybe you should you may see it. Okay, and if you see it, you don't just complain, right? You cannot complain. Say I asked like 2 tough question, right? Because I already tell you. Okay, tell you. Okay, so this is your job. Okay. You shouldn't complain, okay, why I give the test so hard, right? Because I just tell you everything, what I test, right? What I test. But the only reason is that maybe you're not serious enough in this class. Okay, so and for this type of class, and if you're not serious, and you won't get anything from this class. Okay. So if you want a career in data science, machine learning, or whatever, you have to take this, and you want to make progress in that field, you have to take this class very serious. Okay, because all the meat here. It's a pain to learn those things, but eventually it will help you a lot. Okay. Okay, so we do have other property, but 3 and 4. But if you're curious, you can always Google. Okay, this is very popular property. Here another also set a very famous property, the continuous mapping theorem. Okay, CMF, CMT. Okay, continuous mapping. So in the continuous mapping theorem, it tell you. So for a simple case, okay, for a simple case, basically like if you have a conversion in a probability, estimator. Okay, which is a theta n hat. Okay. Maybe the mean or the sample standard deviation or whatever, okay, and it converts to a true value, okay, the theta. But sometimes you don't just look at that estimator, right? That statistics. Sometimes you need to do something with that, right? Say you need to do a function, right? A transformation on that, right? Which you use a G, you apply in that statistic, right? Another time, if your G, okay, is a continuous function, okay, a real value function, and continuous at theta, okay. And the beautiful thing here is that like we can show that the continuous mapping theorem will tell you that the G of theta n hat also converge in probability to G theta, okay, G theta. So say if you have a sample mean, right, it converges to the X bar, converge to the mu, right, and now say I don't look at X bar, but instead I look at maybe X bar square, right? So basically like X bar square, it will converge to mu square too, right? Maybe X power to the 3 or to the 4 exponential X bar, it also converges in probably to exponential of mu, okay? So it will be beautiful property, right? I say, if you talk about the proportion, right? You have X bar in the proportion case, right? Which is the proportion, it converts to the P. And then you can see, if you do maybe X bar times 1 X bar, right? It also converts to P times 1 P. And all those things can be applied, okay? And actually, we do have the more general result, okay? Which it tells us actually it can be extended to the k-dimensional random vector. Okay, so the xn is a k dimensional random vectors. Okay, and G a function from k dimension to L dimension. Okay, and it's a continuous function. And if you have the conversion in property from xn to x, okay, and then a G apply on xn, it also converts to the gx. And if for the conversion in distribution, it holds true, right? It holds true. We do have the version for almost sure conversion, but because we in this class again we just look at these two conversions, right? So here we just provide it here, okay. But if you Google the continuous mapping theorem, you should be able to see this kind of a very nice property. Okay, nice property. Okay. Let's maybe just look at the proof for the one-dimension case, and why is the case, right? Why is the case here? If you have the theta n hat, right, converge to probability in theta, and then G theta n hat conversion in probability to G theta. Okay, and just maybe look at this simple case, okay, and other case, and then for the general result, it's kind of similar fashion, but now you need to look at the distance a little bit different. Okay. But we just do a simple thing here, so you have a sense of what it is actually about and why that's the case, right? So maybe I do insert a slide here. Okay, so I just look at the one-dimension case. Okay, 28 here. So it tells us, right, if xn theta n hat, okay, xn theta n hat, it doesn't matter, okay. Just a truth, right? It converts to the truth here, theta here, which is unknown truth in property, then g of theta n converge to g theta in property, okay, probability, okay. So basically the goal here is that, okay, the goal here is that, so basically we need to prove that, again, for any epsilon non-negative, right? And the property of g, the distance between these two, right, to g and theta greater equal epsilon go to 0, right? So basically, like, you know, they're not far away. They shouldn't be far away, right? And for any epsilon non-negative, and if they far away more than epsilon, that's with very low probability, right? Or maybe in the other direction, you can think like the probability they getting close shrink by epsilon distance, getting very big, right? Big, right? Which is close to 1. So basically, like, if you remember the continuous continuous function definition, right? And recall that, right? G continuous gx g dot, okay, whatever, at theta. Then for any epsilon positive, right? Then exists, right? Exists. This is exists notation, right? This is for any, right? For any. This exists, okay. I just want you to, you know, on the same page, right? Because you know, sometimes your instructors previously may not use the same notation as I was using. Maybe I just put exists, okay. So this way is this sigma delta, right? Delta non-negatives, such that, okay, if you have x subtract theta less than sigma, then gx, right, subtract g theta less than epsilon, right? Epsilon. Okay. So this is the definition of the continuous distribution, continuous function at a point, right? Theta, right? You know, you all know that, right? Probably, yeah. In calculus 1, okay, calculus 1. And so since now you see why you need to learn calculus, right? They all related, okay. If you go to a certain level, you see basically they all related, okay. But some, you know, sub at the back, okay. Some it kind of move in front to help you see application stuff, right? So basically, like, because of that, right? So now you can see that this property g theta n, g theta will be less than equal, right? Interesting. Because this transition, okay, delta, okay. Think about this, okay, but it's true, okay. And because this, and know that, right? Know that. But maybe this is, and this quantity, if you convert to 0, okay, because theta n convert to theta in property, okay. Right. Maybe I make it like this, okay, convert. Okay. So basically we show that this is because of maybe I put maybe 1 here. Okay, so this because of 1. Okay, because of 1. Okay, 1. Okay, so put here. So this way, when you go home, if you see clearly, it should be it's good now. But if you don't really digest it and then think about that. Okay, because of this. Okay, because of this direction. So basically, like this relation. So basically, now you can see that. Okay, see that. You can see that. Okay. And so basically, like we did show that, right? R G theta n hat conversion in property to G theta. Okay. So this is called continuous mapping theorem. Okay. This is a very powerful theorem in statistics. Okay. Because when you derive a distribution for something, right? And basically, like you can apply, and you know that that distribution, right? That statistics converts to something, right? And basically, you can apply any continuous function, right? And to get the conversion that that function scale, right? You can like x to the 2, x to 3 square root of x or something like that, right? And maybe exponential of x. So this is called continuous mapping theorem. Okay. And with that, okay, with that, and especially with the version here, okay, the multiple version here, the general version here. So it gives us a lot of things. Okay. So one thing is that some properties here. Okay. So first and first, there are one other important property where it tells that if you have theta n hat here an estimator, okay, it converts to theta, and gamma n hat conversion to gamma, and both here conversion in property. Okay, then a joint will conversion in property. Okay, so this is a very beautiful property. You have the marginal conversion in property, and the joint will also conversion in property. So it's not always hold for all kind conversion, okay? But at least for conversion in probability, it hold. So you have the marginal conversion in property, and the joint can also conversion in property. And say if we accept this correct, okay, this correct, and then basically we do have the proof here. Let's see. Today my plan is that I want to complete the night 3. Okay, so maybe I don't have enough time to go over everything. Okay. So my plan is that, let's see if I can make through whole here, because this is a long chapter, and then okay. So basically, okay. I will do the proof. Okay, one more proof, and then from that, because everything important here. Okay, this thing is a long progress of evolving of statistics. Okay, they're all very important results. But the problem here is that if we stuck too long, and then we don't have enough time to do other, you cannot see the applied perspective eventually. Yeah, this is kind of missing this. A lot of people who teach this class, they get in trouble too, because you stick too long with the theoretical, and then you cannot see anything about the applied perspective. So we try to avoid that trap. Okay, but anyway, but if you do too apply, and then you get to the trap where you don't know why this thing going confirm, right? And you pretty much you're not different with an engineer person, a software engineer. They know a lot of things, but they don't really know what the underlying thing. So we will have to have a balance that. Okay, so here it's very important, right? Because now you only have marginal one, and then you get the a John 1 version. Okay, and say if because say the John 1 work, right? The John work. So basically now you can see that if you apply the continuous mapping theorem, the CMT again, we know as CMT. And then at a time, if you look at the function, right? The G each of the makes the two components to the summation, right? To the product, to the quotient, right? Ratio here. And basically you also get theta n hat plus gamma n hat conversion in property to theta plus gamma. The time also will follow the quotient or quotation? I just put quotation. Quotient. The A, but this is the product, right?
Yeah, that's the quotient.
Quotient. I just want to make sure I use the right one. So it won't confuse you guys. Okay, so say because of that, right? Because of the top, you get the joint converge in probability to theta gamma. So basically now you can apply the continuous mapping theorem for the continuous case, right? And with the function, either summation function or the product function or the quotient function here, and you get all these things, right? All these things. So it's very beautiful, right? Very beautiful. So let's just look at the proof here for the property here. Okay, maybe I didn't know it's by star here. We have so many star, but okay, I make this a star here, maybe starfish. So in that one more slide. Yeah, I think that this is the last proof I will do. Okay, I won't do more proof here. In any case, you have you will have the note, detailed notes, so you also don't need to worry much about if you're curious about the proof, right? Property of so basically like let's see theta hat. Okay, so basically we want to show that, right? We need to prove that so we have distance, right? Here we have theta n hat and gamma n hat. Okay, so here is the theta gamma. Okay, n hat, gamma n hat, right? Subtract again. You should know that here we just standardize in some way. Okay, basically just think about like just Euclidean distance. Okay, Euclidean distance. It's not okay. Sometimes we put a two slash, right, to make sure like we know that the Euclidean, the distance. Okay, distance, right? So basically in this case you can show it will less than equal. Okay, so basically now you want to show this quantity go to 0. Okay, this is your goal. Okay, because you now get used to with the conversion in probably kind of proof already. So basically what we want to do is that we want to show this distance, say in a sense of Euclidean, right? It's will go to 0. Okay, now we extend to a two-dimension case. So it can be shown that this guy is less than equal than theta n subtract theta plus, okay, gamma n subtract gamma. Okay, so, okay, it's easy, right? It's easy inequality. Yeah, very easy inequality. And then basically this guy will be less than equal to theta n subtract theta greater than epsilon by 2 plus, okay. I think you did you see this kind of trick a lot in calculus? You see this trick before? Now you see it. Okay, but there's a trick. It's a kind of popular trick. Okay, they take the thing out, break thing out, and with the small epsilon. So I mean, if you do a lot of advanced calculus, you should see this thing. Okay, I did see this thing a lot in my first year in university because my bachelor was in math, also math education. And we have a very good school when they teach very good analysis thing. You are Rudin book. So Rudin is a very good book. So this guy, basically this guy, you can see because he conversion to probability, right, in theta, so which means he go to 0, and this guy also go to 0, right? So basically the total will go to 0. Okay. Okay. So we have theta n hat, gamma n hat. Okay. Theta gamma. Okay. Okay. So it's very beautiful, right? Because you have marginal and then you can get to the joint. So it's just so nice here. Okay, with the joint here, and you can do things like you can add them up, you can divide, you can take a product, right? And you can do all the silly thing with those, right? And the other is a Slutsky theorem, okay? Also one very important theorem, because as long as you need to derive a new distribution, right? A new statistic, test statistic, okay? And then you need to prove your test statistic, right? Your distribution conversion in distribution to something, right? To something. And the continuous mapping theorem, it helps you to do a lot of things by typing or G function. And with the Slutsky theorem here, it also helps you to do a lot of things. Basically, let's say here in this case, it's not as freedom as the conversion in probability. So you need the xn conversion in distribution to x, okay, and yn conversion in distribution to c, okay. And c must be a constant, okay. You have to have like c constant for the yn, okay. And at that time, you can show that xn, yn, okay, each conversion jointly to x and xc, okay, xc. So it's not as free as the probability conversion, right? For probability conversion, you can have like xn conversion to x, yn conversion to y, and then you have the joint conversion to x and y. But now for the conversion distribution, okay, it has to require one of them must conversion to a constant, okay. And after you get that conversion to constant, and then you can show that xn, yn conversion to xc, okay, and xn plus yn converts to x plus c, okay, and because of a, right, after a hold, and then you just type in the continuous mapping theorem, and you can get a BCD, right, BCD. I think maybe I should make it consistent, like what we show that in a what we show as in the previous one, right? Okay. Right. Again, from CMT theorem, right? From CMT, continuous mapping theorem, okay. And here remark, right? The condition here is important, okay, to make the Slutsky theorem work, okay. Otherwise, it will not work, okay. And again, you can always look at a counterexample where say, if you have two conversion in distribution with two different random variables, then you shouldn't get maybe one of these things not hold, right? The joint not hold, right? So here we don't do the proof, okay. So let's us look at some application, okay. So, but here pretty much like a lot of powerful tool for you, to unlock, the new derived estimator, okay. So in case you derive a new estimator, you propose something new, right? Some new test or whatever. This is a lot of useful toolbox, okay. Tools for in your toolbox now from now on, okay. If you stick with this career, okay, maybe do a PhD in this career. So let's see, maybe look at one application, right? One application, because we just look at all the property, right? Now we look at how people they use this thing to make a thing more complicated, right? So previously we did talk about the mean, which is kind of easy version, right? Easy version. You just directly apply the theorem where the variance go to 0, and then at that time you can get the weak Laplace number, right? Which is yn will converge bar will conversion to the mu, right? And truth. But now how about the sample variance, right? The sample variance, right? The sample variance, which in this case you have like yr1 to yn, they are random sample from a distribution where has the mean in mu, okay. The second moment in mu2 prime and the fourth moment in mu4 prime, okay. And so we need the first moment, the second moment, and the fourth moment, they're all finite, okay. And now our job is that we need to show that Sn square is a consistent estimator of sigma square, okay, which is a variance, okay. So this is the goal we need to do, okay. By using all the property we just learned, right? We just learned. So how do we do that? How do we do that here? We have two examples, right? Yeah, again, and then the next one we will also learn to find distribution of this quantity, right? So this is a well-known distribution already, right? We know that, but 935, 9346, it's just like two very, kind of related example, right? How to use the thing we just saw to solve this kind of problem, okay? So for 935, right? So today, February. You like this class so far? You good? You feel useful? Okay. Yeah, okay, yeah. A lot of tricks here, yeah. I have a lot of headache when I learn this thing in Michigan State. Okay, uh, I stay in my office till 1 a.m., 2 a.m. in the morning every day, pretty much. Yeah, and it's the snow, a lot of snow in Michigan, and I need to bike home at 1 or 2. It's a typical schedule. Show up in office at 8, 9, and go home at 1 or 2. But yeah, it turned out very useful, juicy now. Okay, so SN, but you need to have a good balance schedule, right? A balanced schedule. Like you have to break your day, like swim during the middle of the day or something like that. Otherwise, you go end up to some trouble. When I was in Michigan, there one professor, okay, he worked so hard and he didn't do sport. And just one day he had 4% already. And then yeah, he just one day he just run across the hall, yell at everything, do all the thing, and it's not good. Okay, we don't want to run in that situation. Okay, so now we want to show that this conversion in probability, right? Probability it's consistent, right? We want to show it consistent estimator, which means we want to show it conversion in probability, right? Sigma square y1, okay. Any yi, okay, the same, right? Because the ID, okay, ID. So consistent estimator, which means it conversion in probability, okay? So this is a definition of consistent, right? So we have that, okay, xn square equal to 1 over n minus 1. Okay, I rewrite this in one more time, okay? Yi. We can do y bar, yn bar, it doesn't matter, okay? Yn bar just tell you just the average from y1 to yn, okay? So sometimes we use yn bar, sometimes we use y bar. It just tell you the same thing, okay? So know that the yn bar here be equal to y1 plus y2 plus yn, right? And divided by n. And sometimes we use y bar, okay? We can drop that in bar n notation here. But in this one, it can we show that, okay? We show that this guy will be n by n minus 1. So what I do is I type by n on the numerator, okay? And I need to remove that here. From 1 to n, okay. I have a reason for that, okay? But I just do a little bit trick here, okay? So this way, okay. So now you need to verify that, okay? So this guy actually can be written, okay, by this guy, okay? So it shouldn't be any difficulty here, okay? You shouldn't have any difficulty. It shouldn't be difficult, okay? Here you just do the square, right? Take in the square here, and you can collect all the yi here and you should get this. Okay. So basically you get like a sigma of yi square I from 1 to n subtract n of y n bar square. Okay. It's an easy trick. Okay, you just rewrite that. And then after you do that, and basically now the n here come out, and because here you don't have anything, right? You borrow n here, so you can return n here. Okay. So a simple trick. Okay, simple trick. We don't go through walk through that. Okay, because it will take more time if I write this thing again. We already saw this thing already previously. Okay, previously. Yeah, here the interesting part, right? So this guy. This guy, okay, and this guy, right? This guy. So we have two guys, right? So let's talk about each of them. Insert, okay. Yeah, today February 28. Know that, okay? Know that. 1 over n of, so we have two statistics, right? The first statistic is 1 over n of sigma I square, and the second statistic is this guy, right? This guy. And this guy is easy. You know about him already, right? He converts to probability to mu. Right? And the continuous mapping theorem will tell you basically you go to mu square. Is that right? But the first guy, the first guy is it's just the average, right? It's the average of n random variable, right? And each variable now it's become yi square, right? And with the finite is the average. Okay, I just write down here is the average of n random variable y1 bar, y2 bar to yn bar, right? With mean I equal to mu2 prime, right? We did have that in the here, right? The second moment in mu2 prime. And we also have that the variance, right? The variance of yi square will be mu4 square subtract to mu2 square prime, right? Which is finite, okay. So from the which law of large number, it tells us, right? This guy will conversion in probability, right? To mu2 prime, right? To its mean, right? So from the which law of large number, we have the 1n sigma yi bar here, and to n, it conversion in probability to the mu2 prime, okay. Perfect.
Wait, you got that like last one with the law of large numbers?
The which law? So the one which law number tell you, it tells you if you have a sequence. Let me just show you here. Okay, come back. Yeah, let's just show. Come back here. Yeah. Please ask. Okay, this is how we learn, right? Yeah, right. So it tells us, right, if we have population with mu and a finite variance, right, and the average sample mean will conversion in probability to the true mean, right? So this is the which Laplace number. So here in this case, your population now it become y1 bar, y2 bar to yn bar. Okay, it's level up, right? And basically the average of that is also conversion to the mean of the y1 bar, y2 bar, which is the second moment. Okay, the second moment. So it just scale up, right? So say if you do the to the 3 or to the 4, it's also the same thing, right? But basically, like you need to make sure you have the finite variance, right? The finite variance for your population, okay? So which means that you have this guy, right? You have this guy conversion in probability. And because of the continuous mapping theorem, we know that this guy, the CMT, tells us, right? And the which law of large number, it tells us this guy go to mu square, right? Mu square is mu, and they didn't know what, yeah, I think mu, right? So mu square, right? This guy go to mu square already. So which means the two of them, it give us something in the nine. So so we have oh, almost time here. So the Sn bar, right? Sn bar, it converges to the mu2 ram subtract mu, right? It's just sigma squared, right? Right. So it's beautiful, right? So basically, you can show that Sn bar now is a consistent estimator of a sigma square, right? So you think all these things is it's just a toolbox for you to unlock all the property, most property, okay, long history of statistics, okay, and say if you do dissertation, visualization, and whatever any statistic, and you need to write some new tool, okay, and you want to validate the tool, and mathematically, all these important mathematics will keep tasking. Okay, so we stop the class here, and yeah, I see you on Monday, okay, and next class, we try to finish the sufficiency. There are a lot of beautiful things here, okay, and yeah, I mean, if you spend enough time, you start to love it, okay. It's just so addicted, but be mindful, otherwise we get lost in the trap of theoretical. Okay, so stop here. It's